Okay, so this is the first webinar of this series of webinars that I'm going to be doing, and this one is on minerals. So firstly, we are going to look at the first key idea, which is that the Earth is made up of minerals that are constituents of rocks. So we first need to define what a mineral actually is, and these 5 criteria that are listed here are the criteria that you need to be able to say yes or no to if you want to define something as a mineral. So a mineral needs to be naturally occurring. So anything that is made by man technically is not a mineral. So any man-made gems like rubies, for example, aren't technically a mineral. It also needs to be solid in composition, and it needs to be inorganic. So it cannot be the result of any processes of life. Now it needs to have a crystalline structure, which means it has a regular arrangement of atoms. And it has to be pure, which is either as an element or a compound. So a compound is several elements together into a mineral. Now, amber, I'm sure some of you would have thought that amber is a mineral, but amber is not actually a mineral because it is a naturally occurring process. It's tree sap that has been fossilized. So although amber might be classified as a mineral or a gemstone in terms of jewelry, by our scientific definition, it is not a mineral. So what about ice? So ice can be a mineral if it's naturally occurring. So if we've got ice in the form of glaciers up around the poles, that's technically a mineral. However, if we have ice in the form of ice cubes that have been made in the freezer, that's not a mineral. So you should now be able to state the 5 criteria for categorizing a substance as a mineral. Now we know when we classify minerals, they are classified according to their chemical composition. Now there are 7 groups of minerals that you can classify a mineral that you found into. So the name of those groups are carbonates, halides, oxides, sulfides, sulfate, silicates, and native elements like gold or copper, for example. And you can see that in the chemical composition here, there's carbon in this one, hence why it's a carbonate. This one has sodium in it, which is why it's a halide, and so on and so forth. Now, the largest group of minerals is silicates. So about 95% of the Earth's crust comprises roughly around 100 or 1,100 silicate minerals. So these are the most common rock-forming minerals, and they belong to the silicate group. Now, native elements such as gold tend to be quite rare because elements usually combine with the air or water to form compounds. However, only 6 elements occur in the Earth's crust as pure elements. Gold, copper, silver are some to name of. And that's so gold, for example, is always found by itself because it is very chemically stable and doesn't react with anything. So now you should be able to name the 7 most important mineral groups. And you should be able to explain how minerals are classified into these groups according to their chemical composition. Now I am just going to go briefly through the physical properties of minerals. So we know that we use physical properties of minerals that help us to identify them. And we have lots of different characteristics or diagnostic properties that we can use to identify minerals. So we can use color, luster, density, magnetism, streak, hardness, cleavage, or reaction with dilute hydrochloric acid. There are other specific tests for one mineral particularly that can be a diagnostic feature that we haven't mentioned here, like halite, for example. Halite tastes salty, so if you are trying to work out the difference between halite and say quartz, you could taste it to see whether it tasted salty or not. And another one is magnetite, for example, is magnetic, and that is a very diagnostic feature of that mineral. So firstly, looking at color, Color can, in some instances, be a diagnostic feature for a mineral. An example would be azurite or malachite. They have very distinctive colors that really only occur in one mineral. But often, as we know, minerals have come in many different colors, which makes color useless when trying to identify a mineral. So here we have 6 different versions of quartz. We have the quartz, the colorless quartz that is most common. However, we did have smoky quartz that you've seen in sample. We've got rose quartz, we've got citrine, which is yellow quartz, we've got amethyst, which is purple quartz, and we've got milky quartz. So for quartz, color is not a diagnostic feature, but it is if we're looking at azurite or malachite, because color is a diagnostic feature. So not all of the diagnostic features that we're going to be looking at are relevant to every mineral. So streak, as we know, is another diagnostic feature, and streak is the color of the powdered mineral. And it can be very useful when diagnosing minerals that have a metallic luster. So hematite, for example, has a very diagnostic red streak, whereas magnetite has a gray streak, and galena, for example, has a dark gray to black streak, and they make those features are in some cases diagnostic for that mineral. So luster is the way a mineral surface will shine when it's held up to light, and that's called lustre. So we've had a look at some of different lusters in class. Vitreous is a luster where the minerals shine like glass. So quartz is a really good example of a vitreous luster, whereas a metallic luster is where a mineral will shine like the surface of a metal. So a lot of your sulfides will shine like metal. For example, I've got pyrite here that will shine like metal. And the last example that I've got here is what we call an earthy luster, which means it doesn't shine at all. It's very dull. And the example that I've got here is kaolinite. Now, minerals can also be determined or ranked on the hardness of their chemical structure. And that scale is called the Mohs hardness scale, and it is a scale from 1 to 10. And we use instruments, and you've used them already, that help determine hardness. And they include a fingernail, a copper coin, a stainless steel knife blade, and a quartz crystal. So and depending on who scratches what in when you test these, you'll be able to work out what the hardness is of a mineral. Now, density can be a diagnostic feature for some minerals, but mostly it's only really diagnostic for a couple of minerals. And minerals can be identified as being either light, medium, or heavy in terms of density. And the way that you do this is by holding similar sized specimens of 2 different minerals in your hands and comparing their weights. So it really is a relative type of measurement. So galena, for example, is a mineral that's considered to be very dense. And you would have noticed when you picked galena up in the classroom that it is quite heavy in comparison to, say, mica. Gold is actually almost 3 times as dense as galena, and this really helps to deposit gold in placer deposits, which we'll talk about later, due to its high density. Now, cleavage is another diagnostic feature that we can use to talk about identifying a mineral. So cleavage, as we know, is defined as a plane of weakness. Now, some minerals will have multiple cleavage planes and they will occur at different angles, and that's really diagnostic for some minerals. So not all minerals will have a cleavage plane, uh, and that cleavage plane form a flat surface. And if they don't, they have what's called a fracture. So quartz is an example of fracture. It has conchoidal fracture. It fractures in a circular type motion the same way that glass does. And the angle between the cleavage planes is also diagnostic as well. So here at the bottom, we've got mica. In this case, it's actually biotite. And we can see that we've got one perfect plane of cleavage. And it is a perfect plane. You can peel off layers of mica. So it is a perfect plane. And then we have feldspar. This is potassium feldspar or orthoclase, and it has two planes of cleavage that align at 90 degrees. So this is a cleavage plane, and this is also a cleavage plane here. Okay. And then the other one that's really diagnostic is which is calcite here, and calcite has three planes of cleavage. And you can see as the person here in this picture has smashed calcite with a geological hammer, it's broken off in those planes of weakness. So we can see we've got one plane here, one plane along here, and then a third plane along here as well. And you can see that 1, 2, and then 3. Okay, and they're not at 90 degrees. Okay, so another diagnostic feature of minerals is magnetism. Now, this really only applies to some specific minerals, and those are usually ones that contain iron that can be magnetic. So magnetite is a mineral that is strongly magnetic. So we've got a specimen here of magnetite that has nails attracted to it, whereas ilmenite and hematite are weakly magnetic. So we've got hematite here. These are polished crystals of hematite, and you can see that they are at least weakly magnetic and being held together. So magnets can only attract small particles that have been scraped off hematite, whereas sand-sized particles can be attracted by a magnet for ilmenite. Now, the last one that I want to look at is the reaction to dilute hydrochloric acid. So carbonates in particular will effervesce or fizz when dilute hydrochloric acid is placed on a specimen. So this is really a very useful diagnostic tool for calcite. You can see here we've got a sample of calcite and they've put hydrochloric acid on it, and you can see the effervescence, the bubbles in that solution there. So you should now be able to describe for mineral specimens the color, streak, cleavage, hardness, luster, density, magnetism, and reaction to dilute hydrochloric acid. Now again, not all mineral specimens will have diagnostic features in all of these, but some of them will have one or two diagnostic features that make it stick out from all the other minerals, which is the idea or the way that you identify a mineral. Now, ore minerals are found as compounds that we talked about before. So that's two or more elements together into a mineral. So ore minerals either belong to the oxide, sulfide, or carbonate mineral group, and compounds of metals are known as ore minerals. So we've had a look at here, galena, which is lead and sulfur. We've got chalcopyrite, which is copper, but it's also got iron and sulfur in it as well. Sphalerite is zinc and sulfur, and I don't think you need to know any of those other ones. Molybdenum is molybdenite, which is, you can very easily pick that out. It has this very bright silver color. And then we've got pyrite here, which is an iron sulfur mineral. Okay, so when we talk about a mineral deposit, that is a concentration of a mineral by natural processes. Now, an ore body is a mineral deposit where one or more ore minerals can be economically extracted. So the key word there is economically extracted. If it's not economic to extract that ore or deposit, it's actually not an ore body. It's just a mineral deposit. So there are factors that can affect the profitability of a deposit, and these can be divided into two groups. You've got geological factors and you've got economic factors. So geological factors include the grade of the ore. So what's the percent or grams per area of ore? The higher the grade, the more economic it is. The extent of the ore body, so is it very concentrated or is it spread out? The more area that it covers, the more likely it is that it is considered to be profitable. The depth of the ore body also matters. So again, if it's not very deep, if it's quite a shallow, thin ore body, then it's likely not to be profitable. Now, also the difficulty of removing underground water plays an impact on whether you can extract the ore body. And if there's any presence of faults, this could also make it hard for the extraction of the ore body. Now, economic factors include the distance of the deposit from potential markets. So, the ore body, well, I wouldn't call it an ore body because it wasn't economic. I guess the mineral deposit that I looked at for my honours project in geology when I was at university was a copper cobalt deposit up in Central Australia. Now, it was not economic for variable reasons, but one of those reasons is that it was 2.5 hours from Alice Springs. So it was a huge distance. The idea of then going in and mining that and transporting it out would have been huge, which meant that it would not have been very profitable. It also had a very low grade ore as well, which meant that it wasn't very profitable either. Now, the current market price of the material extracted also plays a part as well, because you need to be able to make a profit on your extraction and then selling of the ore minerals. So if your copper price is low, then you've got to have a very high grade copper deposit to be able to make it profitable. And it's also about the availability of energy for processing the ore as well. So if you don't, again, if you're out in a rural area like in Central Australia where I was, we didn't have access to power. We had everything running off a generator. So you would then need to have to run power lines in, and who pays for that? And can you get perhaps solar or wind energy in there? And is that better or more economical? So there are heaps and heaps of factors that determine whether a mineral deposit is called an ore body or not. Now, other factors that I haven't mentioned that also need to be included is the environmental considerations as well. So are you going to be impacting on the ecosystem? Are you going to be, I guess, negatively impacting on species habitats around that area? And also the Aboriginal perspective as well. A lot of the land out in Central Australia, particularly in the APY lands, is land owned by Aboriginals, and they often don't like having you explore in areas that they deem to be historically significant. So you have to go into negotiations a lot of the time about whether you can even explore on their land, let alone dig up an ore deposit or an ore body. And so when we do see advances in mining and ore processing techniques, which we are currently seeing now in the last 10 to 20 years, that does mean that lower grade deposits can be profitably mined if you were to compare that to, say, the end of the 19th century. So the copper cobalt deposit up in Central Australia, as the copper deposits around the world are mined and we need more copper, and the price of copper goes up, and the way that we can extract that copper becomes less expensive, that may eventually turn into an ore body that can be mined. So it really does depend, again, on cost spent versus what's gained and whether we can make a profit or not. So you should now be able to explain the difference between a mineral deposit and an ore deposit.